Welcome to this scientific lecture on negative capacitance in ferroelectric nanolayers, a groundbreaking concept that challenges conventional electrostatics. This is a ferroelectric nanolayer sandwiched between metal electrodes, where spontaneous polarization can create unusual capacitive behavior. Let's start with classical capacitance to understand what we're challenging. Classical capacitance C is defined as the amount of charge Q that can be stored per unit voltage V. The capacitance equals Q divided by V, and for a parallel plate capacitor, it equals epsilon 0 times epsilon R times area A divided by thickness D. In all normal materials, capacitance is always positive. This means more voltage always produces more charge. Here's a Q versus V plot for a normal capacitor. The slope is always positive, meaning dQ by dV is greater than 0. The differential capacitance, which is dQ by dV, is always positive for conventional materials. Typical capacitance values range from picofarads for tiny structures to microfarads for larger devices. Now let's understand why we need negative capacitance by examining the Boltzmann tyranny. Modern transistors face a fundamental physical limit in how efficiently they can switch on and off. The subthreshold swing S equals dV gate divided by d log 10 of drain current, and it must be at least kBT over Q times natural log of 10, which is approximately 60 millivolts per decade at room temperature. At room temperature of 300 Kelvin, the minimum subthreshold swing is 60 millivolts per decade, set by thermal energy. This log current versus gate voltage plot shows the 60 millivolt per decade Boltzmann limit as the minimum slope we can achieve with conventional transistors. This is a major problem because to achieve a large on-off current ratio, we need larger gate voltages, which means higher power consumption. Dynamic power scales as capacitance times supply voltage squared times frequency, so reducing voltage is crucial for low-power devices. Ferroelectric materials offer a radical solution through their unique polarization properties. Ferroelectric materials possess spontaneous electric polarization that can be reversed by applying an external electric field. Here we see a ferroelectric lattice with dipole moments aligned in one direction, creating spontaneous polarization even without external fields. Common ferroelectric materials include barium titanate, lead titanate, and hafnium oxide. The key property is a highly nonlinear relationship between polarization P and electric field E. This is the famous ferroelectric hysteresis loop, showing the S-shaped P versus E curve with memory effects. To understand negative capacitance, we need to examine the free energy landscape of ferroelectrics. The thermodynamic behavior of ferroelectrics is described by Landau-Devonshire phenomenological theory. The free energy U of P equals alpha P squared plus beta P to the fourth plus gamma P to the sixth minus E times P. The coefficient alpha changes sign at the Curie temperature, driving the ferroelectric phase transition. This double well potential shows two stable polarization states, corresponding to up and down polarization in the ferroelectric. At equilibrium, partial U by partial P equals 0, giving us 2 alpha P plus 4 beta P cubed plus 6 gamma P to the fifth minus E equals 0. Now let's derive how negative capacitance emerges from this energy landscape. We start by examining the differential relationship between field and polarization. Taking the derivative, partial E by partial P equals 2 alpha plus 12 beta P squared plus 30 gamma P to the fourth. The ferroelectric susceptibility chi relates how polarization responds to electric field. Chi equals partial P by partial E, which is 1 over the quantity 2 alpha plus 12 beta P squared plus 30 gamma P to the fourth. Here's the critical insight. When alpha is negative near the transition, chi can become negative in certain polarization ranges. If the denominator 2 alpha plus 12 beta P squared plus 30 gamma P to the fourth is negative, then chi is negative. This plot shows susceptibility versus polarization, with a negative region in the middle where the system is unstable. Now let's connect the negative susceptibility to measurable negative capacitance. For a thin ferroelectric film, The charge density is directly related to the polarization. Charge Q equals polarization P times area A for the ferroelectric layer. The voltage across the ferroelectric layer is related to the internal electric field. Voltage across the ferroelectric equals electric field E times ferroelectric thickness TFE. The ferroelectric capacitance equals dQ by dVFE, which equals A over TFE times dP by dE, giving us HE over TFE. Therefore, when Chi is negative in the unstable region, we get negative capacitance. If Chi is less than 0, then CFE is less than 0, giving us genuine negative capacitance. But wait, you might ask, isn't negative capacitance unstable? How do we use it? Great question. Pure negative capacitance is indeed unstable, like a ball on a hilltop. A ball at the top of a potential hill will roll down in either direction, representing the instability of negative capacitance. The answer is to place the negative capacitance ferroelectric in series with a positive capacitance dielectric. For series capacitors, 1 over C total equals 1 over CFE plus 1 over CDE. The positive dielectric capacitor acts like a spring, stabilizing the negative capacitance ferroelectric. This capacitor stack has the ferroelectric with negative CFE in series with a normal dielectric with positive CDE. As long as the magnitude of CFE is less than CDE, the total capacitance remains positive and stable. Now comes the magic: how negative capacitance amplifies voltage internally. When we apply total voltage V across the series stack, it divides between the two layers. Total voltage V equals V ferroelectric plus V dielectric by Kirchhoff's voltage law. Since they're in series, the charge Q must be the same on both capacitors. Therefore, Q equals CFE times VFE equals CDE times VDE. Since CFE is negative, the normal voltage divider formula gives counterintuitive results. The ferroelectric voltage equals CDE over CFE plus CDE times V. If the magnitude of CFE exceeds CDE, then V ferroelectric can exceed the applied voltage V. This is voltage amplification. The voltage inside the ferroelectric exceeds the externally applied voltage. This diagram shows input voltage V being amplified to a larger ferroelectric voltage VFE inside the material. Now let's see how this voltage amplification helps break the Boltzmann limit in transistors. We insert the negative capacitance gate stack into a field effect transistor structure. This shows a negative capacitance field effect transistor with ferroelectric and dielectric layers above the semiconductor channel. A small change in gate voltage gets amplified to a large voltage change at the channel interface. The sub-threshold swing equals 60 millivolts per decade times 1 plus CFE over Cox. If CFE is negative and its magnitude exceeds CDE, then S becomes less than 60 millivolts per decade. This achieves SUB 60 millivolt per decade switching, breaking the fundamental Boltzmann limit. Comparing conventional transistors in red with Boltzmann limit to negative capacitance transistors in green with steeper subthreshold slope. Let's work through a concrete numerical example using hafnium oxide, a CMOS-compatible ferroelectric. Consider a system with hafnium oxide ferroelectric layer and silicon dioxide dielectric layer. Let the HfO₂ thickness be 3 nanometers and silicon oxide thickness be 1 nanometer. The dielectric constant of HfO₂ is 25, and for silicon oxide is 3.9. First, calculate the baseline capacitance if HfO₂ were not ferroelectric. CDE equals epsilon 0 times 3.9 divided by 1 nanometer. This gives CDE approximately 34.5 microfarads per square centimeter. In the negative capacitance regime, we estimate the ferroelectric susceptibility. Suppose CFE is approximately negative 50 microfarads per square centimeter in the unstable region. Then 1 over C total equals 1 over negative 50 plus 1 over 34.5, giving approximately 0.009. Therefore, C total is approximately 111 microfarads per square centimeter, which is larger than either individual capacitor. This gives a capacitance enhancement factor of about 3.2 times compared to the dielectric alone. Now let's calculate the voltage amplification for this specific example. The ferroelectric voltage equals CDE over CFE plus CDE times total voltage. Substituting our values, VFE equals 34.5 over negative 15.5 times V total. This gives VFE approximately negative 2.23 times V total. We achieve a voltage amplification factor of 2.23, meaning internal voltage is more than twice the applied voltage. This visualization shows the external voltage being amplified by a factor of 2.23 inside the ferroelectric layer. Let's calculate how this impacts the transistor subthreshold swing. The negative capacitance subthreshold swing equals 60 millivolts per decade times 1 plus CFE over Cox. Assume a typical gate oxide capacitance Cox for comparison. Let Cox equal 40 microfarads per square centimeter. Then SNC equals 60 times 1 minus 1.25. This gives SNC equals negative 15 millivolts per decade. Taking the absolute value, we get 15 millivolts per decade, which is 4 times steeper than the Boltzmann limit. The magnitude of SNC is 15 millivolts per decade, well below 60 millivolts per decade. What does this mean for power consumption? Let's estimate. The new supply voltage could be reduced to 0.25 times the old supply voltage. The new power consumption is 0.0625 times the old power consumption.